Let us start with some reminder what happened last time. Oh, okay, it's not very good still. So here is going to be a reminder. Last time we were constructing a process, basically on a unit segment, but more generally on the whole half line, positive half line. So we wanted a process xt with continuous trajectories, Gaussian centered, with covariance just minimum of S and T, and continuous trajectories. And it was an intuition that it must be xt, you know, in any orthonormal basis, basically a reasonable one, whichever you wish. So it must be that this representation holds where psi are just standard Gaussians, identically distributed. And these functions are nothing but primitives of this basis. So this is an orthonormal basis. Right? So then what happened? I just took a standard, well, the basis that I like, you know, being educated in pure analysis. So I just took this to be Fourier. And this led us to the definition that, well, to an idea, but basically we used it as a definition of the Brownian motion via this sum. But then, of course, there was a question. So I can write this expression at least formally, but I have no guarantee it converges, right? So the problem was how to know that this formal sum, at least if we do not know anything about distributional spaces. So if we know, then we can think about this as an element of some Sobolev class with negative index. But if I do know, that the question is whether it converges, and it was some lemma, that it indeed defines a continuous function almost surely, right? It was some summation over blocks. And that, yeah, question? Nope. And then, well, I just let it to exercises. Still, there is a question, why do I know? Of course, it's, oh, it must be xn. Of course, it's center Gaussian. So it must be xn here. Sorry for this. Here. Of course, it's center Gaussian. But in principle, so it is needed to be checked that I indeed have the correct covariance, right? And to check that it has a correct covariance, basically, what you say is that once I already know that this converges, then I can just multiply, just open all the brackets, right? And then this is nothing but st plus sum over integers 2 sine pi ns pi nt over pi squared and squared. So this is a perfectly well-defined series. And it's computable, right? This is some exercise in Fourier analysis. And then you just compute. I mean, to make everything rigorous, you just compute this sum and see, okay, I indeed constructed what I needed. If we didn't have this motivating discussion, then this is, a bit magic. Why at all should I write exactly these coefficients, right? Exactly pi n, square root of 2. How did I guess this expression? But in fact, it's fairly general, right? So I can start with any reasonable basis I wish. And of course, if I'm able to prove that here this series defines a continuous function, then here it should be just a formal check. I mean, it must work in any basis. Okay, good. And then let us discuss several basic properties first. So and then this is a definition on the unit segment, and then we just glue several copies one to another to construct the process on the half line. And again, the check of the covariance is very straightforward. Okay. Basic properties, invariance under scaling and inversion. So there is a simple lemma, or maybe proposition. It contains almost nothing, but that's a very important statement. So proposition is that first, for any scaling factor lambda, if I just scale the space by 1 over lambda and simultaneously scale the time by lambda squared, then what I have is exactly the same process in distribution. Note that it doesn't look like, something immediately following from here. Because here the construction is quite specific for 0, 1, right? And here, when we scale, it's not easy to say what happens with such series. And the second property is, that if I define another process to be basically b1 over t multiplied by t, so t positive and yes, like here, so I just define it to be 0 at the origin, then again what I have is my Brownian motion. So what is the proof? Actually, the proof uses, it doesn't appeal to any explicit construction of the Brownian motion. The proof is very similar. So we know, say in A, we know that both sides are Gaussian processes with continuous trajectories. And just a technical comment, so maybe it's slightly more rigorous to say here almost surely continuous trajectories, right? But I prefer, to use another viewpoint. So I define this BT, and on some set of full measure, it gives me a continuous function. Then I just take the complement of this set. Okay, it might be measurable, might be not measurable, and define BT on this complement to be, identically 0. So that it is defined on the full probability space as a continuous function. Is clear what I said? This is just a very technical comment. So that not right here almost surely. And so it's defined on the full probability space. So both sides are Gaussian processes. And we know that if we take any subset of rationals, or maybe dyadic rationals, so for and for any finite subset of rationals, I know that these is distributed, has the same law as just B. This is a straightforward computation because I can just ask, okay, what is the covariance matrix here? And it is scaled in the correct way. So I have here lambda squared, but then there is 1 over lambda to the square, because this is the variance, right? So they're just the same Gaussian vectors. And because of that, I can say that if I consider only rational times, then this is again the same distribution. This is called Kolmogorov's extension theorem. And here why I'm focused on rationals, because I don't like to have problems with sigma algebras. I mean, rationals is just a countable set, and I'm just, I'm not forced to think what is the sigma algebra here. And then I say, okay, the trajectories are continuous. Because of that, so I use these continuity properties. Then basically I'm done. So there is absolutely nothing deep here. The only issue is it might appear if you think about, okay, I have two random variables with values in the space of functions, and then I would like to say that they're the same in distributions. Right? And I do know that all finite dimensional marginals are the same in distributions. Actually, what do I know about the variables themselves? There is some issue with measure theory. But if we are in a countable setup, then there is no problem. Okay, so this is A. And of course, B is exactly the same. So let me prove it here. So first, you say that still, obviously this is a Gaussian process, because if I take any finite linear combination of values, then it's Gaussian. It's still a linear combination of some Gaussians. So this expectation, of course, is 0. This covariance is of course what it should be. STS meaning ST, 1 over T, 1 over S, which hopefully is just meaning of ST. Right. There is a small issue with the origin. So first, this is for positive. By definition, this is just 0 if one of them is 0. And because of that, we see that the covariance structure is correct, but it might be some issue with the continuity of xt at 0, right? Some small issue. I'm going to write it. A priori, we do not know that this process is continuous at the origin, right? So what I can claim from here is that x for t positive, strictly positive, is distributed in the same way as bt for t strictly positive, right? And then basically what I'm saying, what I can say from here is that, okay, well, I do know that the trajectories, these trajectories, are continuous at the origin, right? Not a problem. I do know that, oh, yeah, that's right here, at least for rationals. I do know that these trajectories are continuous on 0 plus infinity. And I do know that they are identically distributed. So because of that, I can say that this xt is indeed continuous at the origin. Okay, almost sure. So just what happened? It was some technicality. I mean, a priori, I was intended to say everything is exactly the same, both sides are continuous on the whole half line, and on rationals, they're identically distributed. Some issue is that a priori I do not know this guy is continuous. But what I'm explaining is that this is not an issue at all, just because, all right, so this is a continuous function, which has a limit at 0 along rationals. So I know that this is continuous, and I know that the limit along rationals is 0. And then it just means that there exists a limit which is 0. And once I know that this process is indeed continuous on the whole half line, then okay, that's just a triviality.
Why is the limit over rational is 0?
Because I know that they're identically distributed. I just constructed them over the set of rationals, and I know these for bt, because bt is the standard Brownian motion. And then I have a continuous function which tends to 0. I mean, yeah, continuous function which tends to 0 along rationals. The only option is that, you know, it has a fair limit. Okay. So the process is indeed scale invariant, and this another property is that it is invariant under inversion. So the intuition you can gain from here, is the following. So for instance, if you are interested in local properties of BT, say you ask whatever, any question about local behavior near the origin, it's always the same question as an asymptotic behavior at infinity, because you can apply an inversion and rewrite everything in terms of t close to infinity. So for instance, if you if you ask about the modulus of continuity, say, of bt at 0, this is basically the question about how fast bt grows at infinity. It's just the same. Okay? So remark is that local properties 0, they are in one-to-one correspondence with asymptotic behavior at infinity. Good. Okay. Now the next standard thing to discuss is the Brownian bridge. So what is the definition? This is the process that I'm going to call the Brownian Bridge. And I'm going to define it as follows. So this is just BT conditioned on the event, okay, it vanishes at 1. And this is not a very good definition. So this is very intuitive, but not very good. Why? So first, what is the intuition? The intuition, okay, I had some trajectory, some graph, and I pin it at the point 1. The problem is that you might guess that this is an event of 0 probability. Just because B1 is the standard Gaussian, right? So and I'm trying to condition on the event of 0 probability. So better to say that I take a limit when epsilon goes to 0 of these distributions when B1 is less than epsilon. Okay, this is a good event. I can condition on it. Then I have some probability distribution, some measure, probability measure on the space of paths. And then I can ask, okay, well, this is the limit in distribution. Actually, I don't know how I should write it. Okay, in distribution. And then I can wonder if there is a limit in distribution. Then probably I should prove something, right? So I just wrote this definition, but it should be some argument why this exists. Okay? So, work. Why does this limit exist? Let us just come back to the original construction, to the construction of the Brownian motion in some basis. So, recall we had this. I'm again forgetting xi. So we had this, and in this particular construction, so it has an advantage, the following advantage. So the first basis function was just the constant, right? So because of that, it was t, and everything else vanished at 1. So B1 is exactly xi naught. It's just identity. Okay. Now the picture is, absolutely clear. I'm just conditioning, so I had many independent variables, and I would like to condition on the event that one of them is 0. Well, okay, not very good, but I can write it this way. Obviously, the limit exists, and just given by this. Okay. Epsilon is just given by the rest. Are there any questions with what happened? And so if, there are several approaches to the Brownian motion, how to define it. For instance, one could start with just saying that this is the limit of random walks. and proving first what is called Donskir's invariance theorem. Then here there is some subtle point how to do this. If we just started with this construction, with this representation, then there is no point at all. I mean, this is just here, just in the blockboard. Okay, so this is indeed well defined, and what is the lemma I need? So there are several facts. Let me continue here. Again, say another proposition. So the Brownian bridge is distributed, I mean, is the same in low as bt minus tb1. Actually, in our approach, this is just a tautology. They are not even the same in distribution, right? They are indeed the same. If this guy is constructed from that, they're indeed the same. Okay? Nothing happened. I just subtracted this term. But again, one could adopt another viewpoint and just construct this as a Gaussian process with some particular covariance, which is easily computed from the covariance of the Brownian motion. And then this is, the statement in distribution. And B, this is 1. This is symmetric. There is nothing to prove here because, okay, these processes are centered Gaussian. With continuous trajectories and covariance. What is the covariance? Okay, this is minimum ST minus ST. Well, for A, this is just a computation, and for B, the only thing you need to check is that this is indeed minimum of 1 minus S, 1 minus T, minus 1 minus S, 1 minus T. I hope this is true. Some identity. Or you can check it from the explicit construction because, again, this function, you can use the symmetry of signs and just check it from here. It's just some very easy, very simple fact. Okay, good. So we have this object. And the next thing I plan to discuss is continuity properties of these trajectories. So if they are, say, differentiable, the answer is no. What is the exact modulus of continuity, etc. Before that, is it number 3 or number 2, by the way? I don't remember. It's number 3 probably. So before, I also would like to discuss another construction which is called Levy. I'm not sure, I believe Chelkak, but well, he's Polish, he was Polish. Chelkak construction. Of the Brownian motion and continuity properties of trajectories. So if it's still a reminder, yes. As I mentioned last time, this approach with the Fourier basis is not very standard in probability textbooks. And what is usually done there is different. So, okay, let us discuss another construction. It fits the same framework perfectly. So what is the construction? Last week I assumed that everybody knows about trigonometric functions like sines, cosines, something very, very made. And now we are going to use another basis, which is also, fairly standard. So Haar basis in L201. By the way, how many of you do know what are the Haar functions? Just raise your hands. Okay, half by half. Good. So F naught is just 1. And then I'm going to use Kn, sorry, double index Kn. It's not very easy to write, so never remember. +1, -1, 0. It is mostly 0. And then I'm, let me just K minus 1. Over 2n, K over 2n. K over 2n, K plus 1 over 2n. Otherwise. So n is just positive integer, and k is odd and less than 2 to n. K, 1, 3, etc. to n minus 1. It's much easier to draw a picture. So what is the picture? The picture is here. So this is just 1. Then what I have is this step function on the level 1. On the level 2, I have 2 step functions like this, and so on and so forth. And it should be a normalizing factor in front, because right now, if you compute the L2 norm, it's just 1 by the length, and the length is 2 to n minus 1. 1 over 2 to n minus 1. No, 1 over, yes, 2 to n minus 1. Must be like that, right? Yes. This is just to make the integral to be 1 of f squared. Well, there is something not absolutely trivial here. So what is trivial is that all these functions are orthogonal to each other. If you multiply any two of them, you have 0. This is a proof by a picture, right? So this is not a formal proof, but okay, just write it down by yourself. Okay, what is trivial is that they are orthogonal. What is slightly non-trivial is that this is a complete family. That actually there is nothing in the orthogonal complement. So here in this word basis, there is some teeny piece of information. Okay, good. And then this is the basis. And what I'm going to do, I'm going to repeat this construction in this basis. Okay. So one can define BT 0, 1 using this basis. Kn, and here let me write GKNT. So what is GKNT? I'm not very good with writing formal definitions, unfortunately, as you might notice. So because of that, let me just draw a picture. And this is the place where formal definitions, are not very helpful anyway. Just think about 3/4. This is not a very bad approximation. Then if you take the primitive of, say, this the last function, then what you see is this graph. Okay, what is the height? The height is 2 to 1 over 2 to n plus 1 over 2. Maybe better to put minus here. It's the same. I mean, this is, an extremely simple function. And now what I'm going to do, I just, run the same procedure. I'm just summing these functions with random coefficients. Random, identically distributed standard Gaussians. Okay? And again, there is, and this is on 0, 1, this definition. Afterwards, I can prolong it, just glue several copies as before. So, okay, this is on 0, 1. Then, of course, it should be an ingredient, so I should know somehow why this is a continuous function. I should have an analog of this lemma on Fourier series I had last time. So there is a simple lemma which says that almost surely this defines a continuous function on 0, 1. So why? Let us just denote by GNT this sum in what's here. And think for a minute about this sum. So first, why this construction is actually very natural and quite beautiful. So first, these inputs on the level n, they act in spatially separated places, right? So I mean, here there is a variable indexed by k. Here there is another indexed by k minus 2. But actually, you know, they're totally separated. So because of that, if it's fairly easy to say what is the probability that the infinity norm, meaning the maximum, over the interval, it's fairly easy to say, for instance, when it's large, right? Because this infinity norm is nothing but the maximum over k of these psi k's, right? So this is just the identity multiplied by something by 2 minus n plus 1 over 2. So they are all standard Gaussians. So they're all of order 1. Because of that, I do not expect they're much larger than 1. So, okay, what I'm going to do is to estimate this probability. There is some information encoded inside. So first, it was the reasoning that the maximum of this function is just the maximum of coefficients, right, with this factor. Then I would like to say it cannot be very, very large with reasonable probability. And by very large, I mean adding here square root of n, multiplying by an additional square root of n, and choosing here another constant that I'm going to fix later. I think it must work, right? So what is, I mean, let us bound it. So of course, this is just less than 2 to the n, which is the number of k's. I'm just saying that the maximum is greater than something if and only if one of these guys is greater than that something. It should be 2n minus 1, but then I'm going to lose another 2. So what's here? And here is the integral of the density of the standard Gaussian. Right. Infinity. Like that. If it's clear, what happened? I had 2 to n minus 1 variables. So for each of them, the probability is here. I have here another factor 2 to n minus 1 multiplied by 2 because it might happen that this is very positive or this is very negative. So here 2 to 2 minus 1. And what I need to say that this is a very small number. So what is the standard estimate for this integral? Just fact. If I have an integral, this error function, and I would like to estimate it from above, yeah, strictly less, this is 1 over a. And the same. An easy exercise. This holds. So I apply this bound. What does it tell me? It tells me I have 1 over c square root 10 and hopefully exponential decay minus c squared, right? Now this is less than exponent log 2 minus c squared. And now I can choose c so that this is negative. Well, I think about c as a big constant that I tune along the proof, right? So this is a big constant. Big, large enough. So that this is negative. And if it's negative, then again, there is no problem because I'm in a position to apply Borel-Cantelli. Right? So I have some events, some bad events. The probability of them decays exponentially. Because of that, only finite number of them can occur. So. And the proof is finished as before. Technically, it's even easier than what I presented last time in the Fourier basis, because it was this estimate of trigonometric polynomials, which you might be not very comfortable with. And here, okay, everything is totally clear, though there is another issue with the fact why this is a complete system in L2. We need to know something. So now let us make a break, I think. Or maybe let us shift it a bit. I'm sorry for that. So let me just say the last sentence. What is particularly good in this construction? And I'm going to start discussing this in the next half. Let us think about the value of this process at some dyadic rational. Say at 3/4. Which of these functions of these j's are non-zero there? If you think for a minute, then you immediately see that all that below the level 2, all that have large indices n, they does not infer this value. Right? So it means that if you would like to construct your process on dyadic rationals, say until the level 10, then what you need to do, the information you need, is only the values of these variables until the level 10. And that's it. Okay, so let us make a break and then discuss it a bit more. No? Okay. Okay, let us then start. If everybody just sits, and waits. It was a concluding remark just before the break. Let me repeat it. So with this definition, what is very useful is that the value at any given dyadic rational is fully determined by the values of these random coefficients up to the level of this dyadic rational. Okay, it's clear? So remark. For any, whatever, p over 2m, dyadic rational, p over 2m, p2 minus m, is fully determined by xi1, formula xi11, xi12, xi32, etc. up to the level m. In particular, if you just do not know anything about analysis like Fourier calculus, etc., you can compute covariances on the edge rationals just by simple combinatorial arguments. So exercise compute this covariance using this definition. Well, this is not, I mean, this is not very hard, so not, not a one line. So there are some inputs, you should sum them. Okay. The only point here is that this is a very natural way to define this distribution on the edge rationals. Yeah? So you can just imagine like iterative procedure to sample BT. Just sample psi node. This gives us some linear function. Okay, not a very good approximation, though still. Okay, some information because we know now the Landin value, the value at 1. Then sample psi1, psi1. It gives us the values at 0 and 1, which are exactly the same. So what is good is that it is consistent along the way, right? So this is exactly the same value and some other value here, like here. Okay? Then you sample the next level. Then what you have, so it was consistent. Then what you have is something that's consistent with the previous step again. Something like here, etc. Good. What's next? So now I'm moving on the continuity properties, and the very basic theorem in this subject actually, which is again at the end of the day not very deep, but it was a big surprise somehow when it appeared. So this is due to Paley. Well, not a big surprise, but let me say a word on it. Zygmunt in 33. It says that almost surely this trajectory is nowhere differentiable. Of course, nowadays, differentiable. Of course, nowadays, this is just, the very classical and actually quite simple fact. You should remember that at that time, the existence of functions which are not differentiable at any point, okay, it was known, of course, but still it was not considered as a natural object, such functions. So it was a time of differential calculus, etc. And here there is, what we see is that we are forced to consider such functions. So moreover, for any alpha greater than 1/2, the probability that okay, it's better to say in words as usual. So this is not only nowhere differentiable, it also has no alpha Hölder points, provided alpha greater than 1/2. So let me put it for any t, the upper limit when whatever h tends to 0, bt plus h minus bt over h to alpha, right, is infinity.
It's not true for alpha equals 1/2.
Well, it's definitely true at any given point. It's a shame. Well, it's a shame that I cannot answer in a second if it can be an exceptional point. So this is definitely not the case at any given point, and we will see it. So we're going to discuss it in more details, the case 1/2. So, but okay, it was a good question. So what is important here, let me say it right now, is that for any t is inside of the probability. So there is a tricky issue. We are working with an uncountable set. The process is indexed by an uncountable set. So if it was countable, then of course there is, and the probability is 1. So of course, if it was countable, then it doesn't matter if you say it for a concrete time or for all the times simultaneously, right? Because it's just the union of a countable number of events. But the R is uncountable, and it makes some difference actually, so we will see it. So let us prove it. And what I suggest is to think about alpha equals 1. I will write it in the general case, but just think about alpha equals 1. So first, it is enough to consider only, say, the interval 0, 1. Because the half line is a countable union of similar intervals. And we know that the increments are the same. So what we need, so what is wanted? We want that the probability I'm going to take negative. The probability that there exists some good point such that this is finite is 0 for any m. Okay? Again, so I can take only countably many m's, so there is no big deal. If I know that there are no good points in this sense, then I know that there are no good points at all on the shoot. Okay? So now what is the idea of the proof? Imagine I have some point t here, which is good in this sense, that the increments do not grow very fast. Okay. Something like here. Then what I know is that I can take several dyadic rationals around. Or maybe let it be this way, etc. And I can think about increments between these rationals. Between this and that, for instance. Between this two. So what I'm going to say is that this increment cannot be too big just because it's less than the increment from t to here plus the increment from t to there, right? So if I know that all increments around t are, are somehow bounded by something, then all the increments here are also bounded. And the only thing I lose is the constant in front. Okay? So now I need more space for this. Oh la la. Okay, let us press it here. So, okay. What I'm saying is that this event, I mean, this is less than m. So it's definitely first, it's enough. I mean, how to say it? So, okay. Let us just proceed formally. So, and for a while I think about alpha being equal to 1. So just imagine we have a nice point. Then, as I told you, the idea is to say that the increment here, the increment there, and the increment there are also not that big. And then use independence. Okay, so what I'm going to say? So what is the probability that b k plus 1 over 2n minus bk over 2n less than, say, 2m by 2 minus n to alpha. So what happened? If I know this is the case, then in the neighborhood of t, I have all these increments bounded by a constant by m. Then I know that this increment is also bounded by a constant by m, and 2 to minus n to alpha. So this probability, of course, can be easily estimated. Why? Because this is the normal variable, the standard normal variable, right? So this is the probability that basically the standard normal variable xi standard normal is less than 2m to 2n over 2 to minus n alpha. This is just the scaling, right? So this is the variable with the variance 1 over 2n, 2 to n. So I should multiply it to 2 to n over 2 to get the standard one. Okay? What is important is that alpha greater than 1/2. So this term is bigger. I mean, it kills the exponential here. Okay, so anyway, this is less than constant, depending on m, probably 2. 1, 2 minus alpha. Okay, now what I would like to say? I would like to say is that if there is at least one good point, then this event should hold for at least one dyadic interval. And I can sum over all the dyadic intervals, right? So, and use the union bound. But of course, right now, I'm going to lose. Why? Just because here, even if alpha is 1, I have only minus n over 2. And I'm going to sum over 2 to n events, right? So I have too many events. But it's easily, one can easily fix it. And the recipe is as follows. So if this point is good, then not only this increment is reasonably small, but also this increment is reasonably small. And the next one, etc. So I can use this procedure more times. So, and say that the probability that the increment, say plus 1 plus m over the increment on the next step is less than, okay, some constant. Maybe depending on k, on m, sorry, to m alpha is also less than constant, depending on m and m, by that. So what is the logic? M small is going to be fixed, say 3. So if this is a good point, then the increment here is also bounded by the same with maybe another constant here. So, okay. And all of them are independent. So as all they are independent, then the probability of the event that for all j from 0 to m this increment is of order 2 minus n to alpha, is bounded by some constant to j to alpha, is bounded by some constant to m plus 1, 1, 2 minus alpha n. Here is the exponent. So why does it help me? Obviously it does, because now if I apply this argument not to the single increment but to many of them, now I have something very negative, right? So now the probability of this single event is less than some constant by 2 to the minus n, minus 2n, minus 3n, whatever I have here. And then I'm going, I can apply the union bound. So let me be slightly more formal. So.
Excuse me?
Yeah, sure.
Independence of what event did you use?
Of increments. So what I'm saying is that, okay, if this is a good point, then this increment is reasonably small. And that increment is reasonably small, but they're independent. Because of that, I can multiply the probabilities. So if each of them is bounded by this factor, the probability, then, you know, keeping track of several of those, I gain here whatever negative exponent I wish.
But still only a finite number.
But still only a finite number. So how to make it a bit more formal? This I don't know. So now how to put things in order. So, okay, given alpha greater than 1/2. First, I find m so that the exponent I have there, this negative exponent, is strictly less than -1. Okay? I'm always able to do so. Then fix constants. Constants Zj in that scheme such that so that this condition greater than, say, 2m in the neighborhood for h less than whatever m to 2 over n, I think. maybe m plus 1, guarantees that all these increments to the right here over b over 2n are less than this constant of j m to minus alpha n. Okay, this is just a deterministic statement. So if I have this, then I have that. So C of j are just some fixed numbers, like 1, 3, 5 for alpha 1 or something else. Okay? Then, okay, note that the probability that there exists some k such that for any j 0 to m, okay, this holds, is bounded by some constant, which is now fixed, to 2 to m plus 1 alpha minus 1 to n, multiplied by 2n. Because this is just the union bound. So now this exponentially decays, and as usual, I just apply Barrel-Cantelli. So by Barrel-Cantelli, I mean, this cannot happen infinitely often. So there exists a level, there exists this, I mean, this n, such that in a very small neighborhood starting with this size, it never happens. But then it contradicts to the fact that there exists a point, where is it? There exists a point where this limit is bounded by m. Is clear what happened? And so what is the most conceptual part? The most conceptual part is that I need some information for any real number. I mean, for any t. Here there is a reduction, basically here. There is a reduction to a countable number of events, to a countable set of events. Instead of considering all t's, I'm just saying that I can consider some events on, say, dyadic rationals that contain my good event. I mean, my event for any t. And then I'm bounding these by Barrel-Cantelli. This is the strategy. Are there any questions? So intuitively, this is a very clear statement because just think for a while. So what is the increment? The increment is a Gaussian variable with variance h. Well, typical value is square root of h. Why at all it should be differentiable? I mean, typically it behaves like the square root, right? So why at all we should have a better bound? Of course, no. And this is just a formal proof that it can't happen nowhere. So the important point is that there are no exceptions at all. Good. Now, now let us prove the sharp result. due to Levy. And this says what is the exact modulus of continuity of the Brownian motion. So, again, almost surely the following holds. So let me, for a given h, here is going to be limit. So for a given limit over h tends to 0 and upper limit. So let me take the supremum over all t, say 0, 1, the minus h of the increments normalized by something. So if the function was differentiable, it should be h here. If I would expect it's Hölder continuous, it should be h to the power of alpha. Actually, the correct normalization is here. So this is h log 1 over h, and even the constant is fairly explicit. Then this is 1. So here, where do we? We're here. Okay, good. So basically, what's written is that the explicit, the modulus of continuity of this function is square root of h log 1 over h. Okay. Again, what is important is the type of this statement. So this deals with the trajectory as a whole. At all the points simultaneously. The supremum here is taken over all t. So, okay, let me before proving, let me discuss a similar statement. So just before the proof. Not a discussion, I don't know how to say, just the tour. One can ask the same question at a given point, right? And all the points are the same, so I can ask this question at the origin. And it was a remark that basically this is the same question as asymptotic behaviors. There exists another theorem which is also a very famous result, which is called Hintschen law of iterated logarithm. So, what's the English spelling of Hintschen? Something like this. He's Russian, so this is not very easy pronounced, probably for you. He was Russian, yeah. Hintschen law of iterated logarithm. It says that if I think about a given point, say about the origin, then the same statement holds. Say bh over something is 1. And what is something? The issue is that this something is different from that we had above. This is exactly the effect I mentioned. So when working with the uncountable set of parameters, you should be careful. So if the set of parameters is countable, then there is a contradiction, right? Because I just can think about countably many points, and if I know that at any of them the modulus of continuity is this one, then I know that the whole modulus of continuity is the same, right? The problem is that I cannot apply the theorem below to each of the points on the interval. And to say that still almost surely, again, this is almost surely, and say that this almost surely happens at any of the points. So actually, this is a rather, involved effect. So it means that whatever point you give me, the speed of growth is here. But at the same time, there are exceptional places where actually the speed is slightly bigger. Okay, this is not a very easy object to deal with. So just okay, an exercise to think why this does not contradict to that. Okay, exercise. There is no contradiction. Good. And then the plan is as follows. We prove the easy bound here today, and the other bound is for the next time. Okay. And the proof of the easy bound goes more or less along the same lines as the proof of non-differentiability. Okay, this is an easy bound. So this is the end of this remark. And here, so here is the proof of this Levy theory. There are two parts, and the part one is why this is actually greater than 1. Or equal. So right, it must be easy. So what I'm going to do, I'm just going to apply, just take h2 to minus n and think about t just k 2 to minus n. So I'm just going to consider many independent increments. Okay, so what is the probability that fix some epsilon positive? So what is the probability that this increment is greater than, 1 plus epsilon by the denominator? This is just a random variable, so normal random variable. So this is the probability that the standard normal variable is greater than 1 plus epsilon to 2 to n over 2. I recovered the normalization. So here there is h is again minus n plus 2 over 2, right? And what is log? Log is basically n. N log 2. So now I need to, well, I just would like to prove that it doesn't happen eventually. So, okay, first, what's here? Slightly lost with the constants. I mean, I don't remember what I should keep track of and what I should not. Wait a minute. So I'm proving that the upper limit is always greater than 1. So I need to estimate all these probabilities from above, right? If anybody follows me. Hello. Are you there? No, something goes wrong, so sorry for this. Something goes wrong. So first, okay, here, first, let us fix it. So we need to prove that this probability is 1. Okay, we need to prove that this happens. So what I'm saying is that, okay, I'm going to prove that the opposite does not happen. So what means the opposite? The opposite means that this lim sup is strictly less than 1. Say strictly less than 1 minus epsilon. So because of that, what I'm going to estimate is the probability that this is less than 1 minus epsilon. Okay. Yeah. Then this is the probability that the standard random variable is less than epsilon. Okay, good. Now it's better. So what is this? This is 1 minus.
Excuse me? Under the root, when you replaced A to H, it's supposed to be.
Oh, yeah, there is no 1/2. No.
Yes.
There is
Just
no.
minus n minus 1, I guess.
So
Or rather
you
1
should,
minus.
Pardon? Oh, that's other way around, right? That's n minus 1. Nope. There is no over. It shouldn't be over n over 2, right? But I'm just puzzled why. Is it clear?
You're
like you give to the root and then you to the root.
Okay, so okay, yeah, okay. What you are saying is that here it must be just n minus 1. Okay, good. So basically, yeah, what's written here is 1 minus epsilon square root of 2. And then log 2, right? And log 2. Okay? If we agree on it? Okay, good. So this is 1 minus integral this to n log 2 to infinity of the density. And probably I'm losing a constant here again. Here it must be 2 because there are 2 tails. Okay? So now what I'm saying is that Okay, what is the probability that this happens for any k? For any k from 0 to 2 n minus 1, we have this bound. B k plus 1 to minus n minus b k to minus n is less than 1 minus epsilon square root of 2h log 1 over h. So nothing very interesting. So this is just this error term we had. To the power 2n, right? Because I have maybe 2n minus 1. Because I have many, many independent events. No, 2n. Okay. So, and what I would like to say is that it cannot happen. So what I would like to do is to estimate this from above at the end of the day. That it cannot happen that all these increments are less than what I need. So wanted some estimate from above. So to get some estimate from above, I think I can just say this less than an exponential of some constant to 2 to the power n minus by this integral, right? Let me denote it somehow, I. And I is just this integral. Yeah. So what I'm saying here is 1 minus x to the power 2n is less than exponential minus 2nx. This is like to say that the logarithm 1 minus x is less than minus x. Okay, good. So I have this bound, and to have an upper bound, I need to estimate this integral from below, right? So we're almost done. I'm still hoping to finish in 3 minutes. So what is this integral? So we already had a bound from above. So another effect is that actually the lower bound is pretty much the same. It's always greater than a plus 1 over a over here. So basically the error function is e to minus a squared over 2 over a. So this integral is 1 over square root of n. And all the constants I kept here. There's 2, there's log 2, etc. And exponential to the square over 2, right? 2 minus n log 2.
1 minus epsilon squared.
1 minus epsilon, yeah, thanks, squared. And log 2. So we are done. Why? Because this is exponential of minus constant over square root of n by 2 1 minus 1 minus epsilon squared. Yeah, that's it. So this is still positive, so even here it grows exponentially, and there is yet another exponential. So what it means? It means that, again, Barrel-Cantelli tells us that only finite number of these events can happen, right? So it cannot happen for all the n's simultaneously. I mean, eventually, right? So what Barel-Cantelli says, and just conclude in words. It says that only finite number of these events happens, meaning that starting with some number, at least for some k, this is greater than 1 minus epsilon, meaning that this limit is greater than 1 minus epsilon with probability 1. Okay? If it fits. I mean, so, yeah. For any given realization, I know that starting with some n here, what I have, I mean, the supremum is at least 1 minus epsilon with probability 1. It means that this limit is at least 1 with probability 1. Yeah?
So what's the purpose of getting all these exponential bounds? I mean, if you want to prove that this is just summable in n, it's just 1 minus a positive number to the 2 to the n. Is what you
here 1 minus what?
Some positive.
Yeah, but it depends on n, right?
Okay. Yeah, sorry.
So.
Yeah, you're right.
I mean, it shrinks, right? So here is the problem. The problem is that it becomes closer and closer to 1, but this power wins.
Yeah.
And you see, well, basically the only thing you should keep track of is this exponent. So I wrote maybe too much. I mean, keeping track of everything morally until here. But the only thing that really matters is here. And you see that this is exactly, I mean, now there is no surprise of why the constant here is sharp, right? So it's very clearly visible because the only influence is here. Okay? Good. So, but this is an easy bound and somehow not very conceptual. So this is a very simple idea. You just estimate what happens on the independent increments. The other bound is more tricky and in fact more conceptual and related to other stuff. So we continue next week. Any other questions? No? Sorry for being a bit messy here. Ask Marianne if you didn't understand some details.